Good afternoon, everyone. So I'm Matthieu Latapy, and I think I'm some kind of Byzantine speaker here because I won't. This is my first slide, and there are already two lies. I won't talk about blockchain at all. I don't work on blockchains actually, and I will almost not talk about financial transactions. But so it's kind of a break before the break for people interested in blockchains. But I will talk about link streams, which is a formalism, a formal framework that we introduced recently, and which I think is very promising for analyzing financial transactions like Bitcoin's exchanges. So what is the kind of objects I consider? First, there is a set of nodes, here A, B, C, and D, which may be bank accounts or Bitcoin users or anything you want. And I observe them for a period of time, here from time 0 to time 10. Okay? And these nodes are not always present. They can arrive in the system and leave the system. So I represent this by a dotted line in front of them. For instance, here, A is always present, but B leaves from time 4 to time 5, and C arrives at time 4, and then leaves at time 9, etc. Okay, so nodes arrive and leave the system with time. And there are interactions between these nodes that take place at some specific times. For instance, here, A and B interact from time 1 to time 3, and again from time 7 to time 8, and B and D from time 2 to time 3, etc. Okay, and this is the kind of objects I consider, and they model very many different situations and many real-world data, which are very important in various contexts, like social interactions, like for instance, you can think of phone calls or message exchanges, network traffic in the internet or on a local network, money transfers between bank accounts, as I said, or between Bitcoin users, etc., chemical reactions, etc. And the question I want to address is how to describe such data. So the idea is I give you a few millions of such interactions over time, and I ask you what it looks like, what the data set I gave you looks like. I want you to describe it in a few lines, in a few pages maybe, okay, with a few plots. And it's not that easy actually. So what do we do in general? Well, we have two big solutions. We may discard the structure a bit of interactions and just focus on the dynamics and look at statistics like the number of interactions over time. And we have a time series or a signal like this. And we are happy with this because we can use our signal analysis tool, time series theory, to describe such a time series. But of course, we miss the structure between the structure of interactions. We don't know if there is a small set. Here, for instance, the number of transactions over time is periodic, and it has nothing to do with the actual structure of interactions. And we can make the converse choice. We can focus on the structure of interactions and forget about the dynamics and just merge all interactions over time, and we obtain a graph like this. And again, this is very smart because we can use all graph theory and network science tools to analyze and to describe this graph. And of course, we obtain much insight on the actual data, but we lose all the dynamic information. So there are much efforts for a few years to improve this situation, to don't have to choose between dynamics and structure, but to study them both together. And the most classical one is to divide the data into time slices, like here, and build a graph representing interactions inside each time slice. So we obtain, this way, a graph sequence, and then we can try to describe this graph sequence. Okay, so the problem with all these approaches is that we have important information loss, even with the time slices. And time slices is a very difficult approach because we don't know how to choose appropriate relevant time slices. Maybe we don't want to have the same time slices for all the nodes or all the time. So there are actually a number of papers just on how to choose appropriate, relevant time slices. And when we do this, when we have sliced data into several graphs like this, we end up with a graph sequence, and actually we don't really have a nice theory, a nice set of tools to analyze graph sequences. So we worked a lot, we lost a lot of data, and then we end up with something we don't know how to describe really. So there is, as I said, there is much work currently to propose other approaches, including, I won't go into much details, but including time-varying graphs or multi-aspect graphs. Also, many people introduce ad hoc properties, mostly related to path properties, contact sequences, relational event models. These are all approaches that try to deal with such objects, both their structure and their dynamics. But in all these approaches, people basically transform the data into some kind of graph or some kind of signal. Okay, and you have to choose between two intuitions. And what we do is quite different. What we say is that the actual object of interest is this stream of links. Okay, that we call string graphs or link streams, depending on the presence of dynamics of nodes or not. So we say that the true object of interest is this stream of links, and that we should deal directly with this kind of data and to define a theory of this kind of objects. Okay, and we have an approach for doing so. Instead of transforming the data into a graph, what we want to do is transform a graph or network concepts, definitions, into concepts on the streams directly. Okay? So we don't transform the data into something that we know how to deal with, but we take a theory we have and we generalize it, we extend it into a theory of the actual object. And we do the same thing with signal analysis or time series theory. We take the concepts of signal analysis of time series and we generalize them into concepts for string graphs and link streams. And of course, it's easy to say. It's a bit harder to do correctly. And in particular, we want to have quite clear features for this theory. We want, I won't detail everything, but we want it to be as simple, as intuitive as possible, meaning that when I define a property, I don't have to work for days to understand the most basic properties. We want it to be comprehensive in the sense that everything I can do with former approaches, I want to be able to do this, then to do it, if possible, easier with this new formalism. We want things to be time and not consistent. You see, we merge two quite big and quite different theories into a unified framework in which there is a node point of view and there is a time point of view, and we want both to be somehow equivalent. And we want this approach, as I said, to generalize graphs and signal. And we want to generalize it in a very precise way that I will detail now. First, notice that there are quite specific streams. The streams which have no dynamics. So you may have a stream where nodes are always present, and two nodes are either always linked together or never linked together. Like here, you have a link between A and B from the beginning to the end, from A and C from the beginning to the end, but you never have a link from A to D. Okay? So we have a string graph where nothing moves, where there is no dynamics. So in this situation, it's completely equivalent to a graph. You encode the same information in both objects. So it's not very interesting in itself, but it gives a precise sense to the fact that we generalize graph theory, because the string property that we want to define. So we define string property on string graphs in general. When we compute them on graph equivalent streams like this one, then we want to find the graph properties back. Okay. So it's a way of saying that graphs are particular string graphs, and the theory we define must be a generalization of graph theory. And we have the same thing about signal, of course. Okay, so I will summarize just to be very clear, because everything we do next is quite formal and quite technical. But just to be very clear on what we do, actually, when you look at graph theory, classical concepts of graph theory, like connected components, etc. Actually, they are all defined from very simple and very basic concepts, which are building blocks to define more elaborate concepts. For instance, connected components are defined from path, for instance. So we do the very same thing with string graphs. We take the very basic concepts from graph theory and we generalize them to string graphs. So string graphs and link strings themselves, you see it's very basic concepts like number of nodes and links, the clusters and induced substructure, substreams, density and path. Okay, and from these basic concepts, we use them to define higher level concepts like neighborhood and degrees, clustering coefficient, betweenness centrality, as I said, connected components, etc. And as I said also, we ensure consistency with graph theory by checking that on graph equivalent streams we have the same properties as in graphs. And we also ensure that classical relations between properties are preserved. In particular, some properties here are defined in the same way and have relations with simpler property, and we want them to be preserved in our formalism. Okay, so I won't detail the formalism. I will just give an example of property which I think illustrates well what we do. It's the density. So the density in a graph is just the probability. Well, there are several ways to see it, but it's just the probability when you take two random nodes in the graph that they are linked together. Okay, so I take two nodes in the graph at random, and what is the probability that they are linked together? It's the density of the graph, and equivalently, it's the number of links in the graph divided by the number of possible links. Well, in a string graph, we say quite the same thing. We say that the density is the probability when you take two random nodes and a random instant, such that the two nodes are present at this instant in the graph, in the string graph. Then the link is present in between these nodes at this time. Okay, and equivalently, it's the number of links in the stream divided by the number of possible links, which is written like this with the appropriate notations. So you see, this is really what I meant by having simple concepts. In my opinion, this is very simple and very natural extension of the classical notion of density. Still, it has the nice property of being equivalent to graph density on graph equivalent streams, and also it has the same usual relation with the number of nodes, number of links, and average degree as in graphs. So it's a good candidate for generalizing density to string graphs. And then, when we have this concept, this definition, we can use it to define, as I said, higher level concepts like cliques. In a graph, a clique is a subgraph, or a set of nodes, such that the induced subgraph has density 1. Okay, it's a maximal density. Equivalently, all the nodes are linked together in the clique. Well, we don't have to work more than that to define cliques in string graphs. We just have to say, because we have density and we have substreams, so we just say that in a string graph, a clique is a substream of density 1. Equivalently, all nodes are connected together all the time, like in this example here, red or pink, where ABC are linked all the time for this time period. So it's a clique in the stream. So the important thing here is that I don't have to make more work to define cliques because I have a good definition of density and actually also of substream. Okay, and this is what we did with many graph concepts. So I won't detail them, as I said. Okay, so we have something like a 50-page paper where we present a broad set of basic graph concepts generalized to a string graph, and I just put the pictures here. And I will end my talk here, just a few directions for future research and a few conclusions on where we stand. So we provide a language in the sense a set of concepts, a set of mathematically defined concepts that make it easy to deal with interaction traces like financial transactions. You see, I'm not such a liar. Combine structure and dynamics in a consistent way, in the sense that nodes and time play similar roles. They generalize graph and network theory, and we are working currently on generalizing signal on the time series. For instance, I would like to define the derivative of a string graph, and I want it to be a string graph, of course. Okay, I didn't say anything about it, but of course we meet classical algorithmic challenges and also new ones related to streaming algorithms and things like this. It opens new perspective for data analysis because you can see our feature, our string graph properties as features for machine learning and for detecting events, for instance, in such data. So we work on fraud or money laundering detection, for instance, and also it clarifies, in my opinion, the interplay between interactions and relations, because graphs model relations, string graphs model interactions, and of course there is an interplay between both, because you have interaction between relations, and relations emerge from interactions. And we study, of course, a set of real-world data related to internet traffic, as I said, financial transactions, mobility and contact between users, mailing lists, sales of on online stores, etc. And that's it. Thank you for your attention.
Concerning probability, use probability for some definitions. But if you speak about probability, then you need also some probabilistic assumptions on the dynamics, so that you can work, for example, with stationary, so that a stationary exists, so that you convert to stationary.
I don't have, I understand, I don't have a model point of view. Actually, I have a data. So I start with a data in a file, and when I say the probability, it's actually the fraction of.
So you assume that there is that a fraction exists on the data.
Yeah.
To exist on the data is different than exists in expectation, for example.
Yeah.
So you need to describe, to give a probabilistic assumptions so that the dynamic model has converges or has stationary marginal probabilities.
Yes, I would.
Use the margin, because this is what you use. You use the marginal probabilities.
Yes, exactly. That's the expectation, actually.
Yeah.
What I would like is more to be able to have quite a long data in time and to answer to the question if it's stationary or not.
Yeah.
No?
And to me it is clear that you use here probability, you make assumptions that are probabilistic assumptions, but you didn't show them. You need them in order to say that you have that a fraction exists, for example. Fraction is the limit of a fraction, because your...
Yes, but I have finite sets.
The sets are finite, but the dynamic is not finite in time.
And the time is continuous.
Yes.
I take only finite time, I mean bounded time.
Yes, so assume that you bound it.
Mm-hmm.
And depending on your bound, then you may have other probabilities. So it is defined only for a given bound.
Sure, it's for a given bound.
This is what you want to do, really. If you want it to be only valid for each time, have another...
Yes, I understand. I think I understand your point, but actually I have a data that doesn't move that I want to study.
Yeah.
Okay, so I have a duration for this data, and indeed there are some assumptions that I didn't tell, that the links are disjoint interval, closed intervals. But with this in hand, I'm not sure I understand the question, but.
You want to do predictions. Then
Yeah.
you go to this problem.
Yeah, so next year maybe prediction.
Okay.
Because actually it's a bit strange, but it's static data. You see, I have my data. I don't generate any data.
Yeah, and also the question is then, in terms of ergodicity, can you take one sample and get all the information from the sample, or do you need a number of independent samples in order to speak about fractions? So is it time average? Is it averaged over a number of realizations, or is it just something you get from one path?
I have just from one instance. I don't have realizations because I don't have a model actually. I just record. It's like if you take.
So the question is whether what is its actual meaning? Because depending, if you have just one sample, then.
Mm-hmm.
But it can be very irregular, but it may.
It may not.
Yeah.
Well, I'm interested, for instance, in saying if in my sample, in my data, I have some parts which are denser than others in this data. No, I'm not clear.
Well,
like in a graph.
Well, just assume that in practice you have only one.
Yeah?
One node, and it is always connected with node 2. And then you run again the same simulation. You have node 1 always connected to node 3.
Yeah.
No more. So what will you do? Is it of interest for us, or shall we just say in one case we got this, and in another case we got this?
Yeah.
So I think that you lose some information if you do that. What you should do is run a number of simulations, and then make some statistical
Yes, I understand.
appearance and description of this.
I think I understand, but and this is definitively something we have to do because it's much more general. But when you have, it's like when you have one graph. If you have a graph, a social network, or I don't know what, you are interested in saying that it has density 0.1 or 0.9, for instance. Okay, it's exactly the same thing we are doing. Or saying that in this graph of density 0.1, there are parts which have density 0.9. So it's
this is part of random graph theory, and random graph theory speaks about stationary behavior of.
Sure. Sure, but in
metrics
graph studies, there are not only random graph theories. For instance, I don't do random graphs, but.
Okay.
Yes, you're right. We need, for instance, random models for this kind of objects, which we don't really have. At least they are not satisfactory.
Okay.
Let's thank the speaker.
Thank you.